You know, you click on things all day, every day. You hit play on a video, refresh your feed, log in somewhere. And it feels completely instant, totally effortless. But behind that one simple click, there's this hidden journey happening at lightning speed across a global network. So today, we're going to follow that click. We're going to uncover the invisible world that makes the web work and see how that very same system can be turned into a weapon.
Okay, let's really get into it. We're going to trace the path of one single click. Let's say it's on a YouTube video. It's a journey that kicks off on your screen, travels down this really complex stack of digital rules, flashes across the internet as pure data, and shows up at a server maybe halfway across the planet, and it all happens in the blink of an eye. We're going to see how this amazing system gets you your content and, maybe more importantly, how it can be exploited to bring the whole thing crashing down.
So to understand our click's journey, we first got to understand the rules of the road. You see, all digital communication, from an email to your favorite online game, it all follows a standardized framework. Think of it like a universal rulebook that makes sure every single device is speaking the exact same language. And that rulebook is called the OSI model. The OSI model is absolutely key. It breaks down the super complex process of network communication into 7 separate layers. Now, each layer has a very specific job, and it only talks to the layers directly above and below it. This is the magic that allows, say, a brand new iPhone to communicate perfectly with a 10-year-old server that's running a totally different operating system. It's a universal translator for computers. So, when you click play, your request starts its journey at the very top layer on your computer and travels down the stack. At each layer, it's like a new wrapper of information gets added on, a process called encapsulation. Once it hits the bottom, it's shot across the network as a stream of ones and zeros. Then, when it reaches the YouTube server, the whole process happens in reverse. The data travels back up the 7 layers, and each wrapper gets taken off until your original request is understood. And that's when the video starts to play. Simple, right? All right, let's zoom in on the very top of that stack. Layer 7, the application layer. This is the only part of this whole process that you actually directly interact with. It's basically the bridge between your software and the network itself. You know, when you type youtube.com into your browser, that's the application layer doing its thing. It uses protocols, which are really just sets of rules for communication, like HTTP, the Hypertext Transfer Protocol, to put together your request. It's essentially saying, hey server, I would like to get the main web page you have. It is the starting pistol for everything that comes next. Okay, so once your request leaves the application layer and starts heading down the stack, it gets to the transport layer. And right here, your computer has to make a really important decision based on what you're trying to do. Does this information need to arrive perfectly, with every single piece accounted for and confirmed? Or does it just need to get there as fast as humanly possible, even if a few bits get lost on the way? And the answer to that question is what's so cool about this. For loading the YouTube webpage itself, the text, the buttons, the little thumbnails, it uses TCP, the Transmission Control Protocol. This one is the reliable one. It does a 3-way handshake to set up a connection and make sure every single piece of data arrives safely. But for the video stream, that uses UDP, the User Datagram Protocol. UDP is all about pure speed. It just blasts the data out there without waiting for a confirmation. Because, think about it. If you miss one frame of a video, there's no point in resending it a second later. The moment's already gone. So yeah, your single click uses both.
This whole system, it's really a masterpiece of engineering. It's designed for efficiency, for a great user experience. But this focus on handling requests so well, it creates a pretty dangerous blind spot. Built right into the design is this fundamental imbalance and asymmetry between the person asking and the person answering. And it's this imbalance that can be weaponized.
This slide just lays it out perfectly. For your computer to send a request, it takes a tiny, almost zero amount of processing power. It's cheap. But for a server to fulfill that request, while that can be incredibly expensive, the server might have to run complicated database queries, load a bunch of files, check your login info, and build a personalized page just for you. All of that eats up a ton of memory and CPU power.
And this quote from Cloudflare just hits the nail on the head. Attackers figured this out. They realized they could exploit this disparity. They could use a tiny little bit of their own resources to force a target to spend a massive amount of its resources with the ultimate goal of just running them dry.
So how exactly does this work in practice? How do attackers actually turn these simple, cheap requests into a digital superweapon that can take down major websites? Let's break it down. This is what's known as an application layer or L7 DDoS attack. And DDoS stands for Distributed Denial of Service. The goal is simple. You flood the target with so many of those expensive requests that it just can't keep up. It's literally like creating a sudden massive traffic jam on a digital highway, bringing everything to a grinding halt and making it impossible for regular people to get where they need to go.
Now, attackers don't do this from their own basement computer. No, they build an army first. They infect thousands, sometimes millions of everyday devices, laptops, security cameras, even smart fridges with malware. These zombie devices then form a network called a botnet. And then, from one central command server, the attacker can direct this entire army to send requests to a single target, all at the exact same moment.
And here's the sneakiest part of the whole thing, the biggest challenge. Unlike some other attacks, each request from each bot looks like a real user just trying to access the website. There are no weirdly formed packets or anything obvious to flag. It's just a tidal wave of what looks like normal traffic, which makes it incredibly between an attacker and a real customer.
So if the attack is specifically designed to look just like a huge crowd of real users, how on earth do services defend themselves? How do you filter out all the bad traffic without accidentally blocking your actual customers? Well, the answer lies in a layered defense.
There's no single magic bullet here. Instead, defenders use a whole toolbox of strategies. A web application firewall, or a WAF, it acts like a really smart bouncer at the door, looking for suspicious patterns. Rate limiting can stop any single person from making way too many requests way too fast. You've probably seen challenges yourself. Yep, those capture tests that make you prove you're human. And then, behind the scenes, services are using things like IP reputation databases to block known bad guys, and huge anti-cast networks to spread the attack traffic out so thin that it basically just fizzles.
Wow! So our simple click on a YouTube video has taken us on a heck of a journey. It's revealed this elegant, layered system that makes near-instant global communication possible. But it's also shown us the fragility that's baked right into that system, where the very efficiency that makes it work so well also creates the vulnerabilities that can be used to break it.
And that leaves us with this massive question. As our world gets more and more dependent on these invisible digital systems, the battle to protect them becomes more critical than ever. It's this constant cat and mouse game, between the people who build the web and the people who try to tear it all down, all happening quietly in the background of your next click.